Welcome everyone to our lesson today on the wave-particle duality of energy and matter. This is our first lesson in Unit 10 on modern physics, which will be the last unit in the Regents Physics course of study that is offered by myself. So today we're going to take a look at how light can be described both as a wave and as a particle depending on how it's going to be interacting with matter. And we know that light is a form of electromagnetic radiation, and we can represent it as a wave being propagated by an interchange of energy between electric and magnetic fields. But the wave model, I should probably change this color here, so I don't have to, but the wave model of light can explain phenomena such as interactions of light with matter. If we're just dealing with electromagnetic radiation interacting with other types of electromagnetic radiation, we can treat light as a wave. But when it starts to interact with matter, when light starts to interact with matter, looking at light as a wave doesn't quite explain all the behavior that we see. Now, in these other interactions, electromagnetic radiation acts as if it's composed of a particle as opposed to just energy, which the particle would then possess kinetic energy and momentum. And in certain instances, it works to explain light in this way, as a particle. And specifically, that interaction is what we call the photoelectric effect. Now, when light, any form of our electromagnetic radiation, strikes matter, some of that light's momentum is actually transferred to the matter. So in theory, if you were to shine a flashlight onto the wall at home, some of the momentum from the light and the flashlight, or making up the light from the flashlight, it's going to transfer its momentum to the wall itself. So in theory, the wall would, knowing the conservation of momentum, would start to move faster. Now, it was discovered in the 19th century that light that's above some minimum frequency, so having enough energy, so nothing that's going to be real low frequency or low energy, and is incident on certain metals, it caused electrons to be emitted from the metal. So in theory, if you were to take a, let's say a steel cooking pot off of out of your cupboards, and you were to shine your flashlight onto that pot, you could essentially eject electrons off of the pot. Now, this certainly doesn't happen, one, because the light from the flashlight isn't the correct frequency, and the metal making up the pot is probably not the right metal, so it wouldn't actually work. But in theory, this is what the photoelectric effect is. So that's what we call the photoelectric effect. And that can't be explained by looking at light as a wave. So therefore, this interaction causes us to treat light as a particle as opposed to a wave. Now, you probably have more experience with this than you think, or at least an idea of how the photoelectric effect works. And the example of that we'll talk about here is a solar panel. And with a solar panel, we essentially have incident rays, or sun's rays, that are incident on a solar panel, which is made up of matter, and the matter contains electrons. And when that matter absorbs sun's rays of the high enough frequency, it causes electrons in this material, or in this case the solar panel, it causes these electrons to be ejected. So electrons are ejected from the material. In the case of a solar panel, we can direct those electrons that are ejected through an electric field. And if we have moving electrons in an electric field, we generate a current, which we can then use to power our home, supply the electric grid, or use it directly to power some type of device. So solar panels work off of this photoelectric effect, which means we can't just use the wave model to explain what light actually is and how it interacts. And we'll look at a little example of this. We have a piece of metal here on the left-hand side of this diagram, and we are supplying a small electric field in this setup from the battery here, which currently has no current being drawn from it. And we have a flashlight that's shining down on a piece of metal here. In this case, it happens to be sodium. And we can change this, and depending what metal we pick here, it's going to interact differently with a different type of light. Now, right now we have a scale selector that can change the type of electromagnetic radiation we can emit from this flashlight from 100 nanometer UV light up to 850 nanometer infrared light. Now with the infrared, I remember this is longer wavelength radiation, and the intensity, if we increase the intensity of this infrared radiation or increase the amplitude of the waves, we bring this up to 100% intensity, nothing's happening here. We don't have a current. We don't see anything moving in this little chamber here. Nothing's going on, no matter how we change the intensity of that light. And that's because, close this, the frequency of the light here has to be above a certain minimal value, depending on the metal it's interacting with, in order to cause electrons to be ejected. Now, if let's say we bring this down to, let's say, it's about, I don't want to mess with that too. It's about 30%, 25, 30%. If we change the type of radiation that we're emitting from this flashlight from the infrared region into the visible light region, we see the color of light that's being emitted is changing. The frequency is changing. The wavelength is changing. Now, as we get to a smaller, shorter wavelength, we're in the blue region now, we start to see some electrons being emitted from this piece of sodium metal. Not a lot, but we do see some being emitted. If we increase the frequency, decrease the wavelength, we start to see a current being generated here and more electrons moving across this region here. Now, we can cause a greater movement of electrons by changing two things: increasing the amplitude of the waves that are being emitted from the flashlight by increasing the intensity, if we bump that up to 100%, we're applying greater energy from the flashlight, which is causing more electrons to be ejected due to the increased energy from the piece of sodium metal. Now, if I bring this back down to about 30%, we see a slowing there. And if I increase the frequency or decrease the wavelength of our radiation here, let's go down to, 250 or so, 200 nanometers, we're seeing a much greater current, a much faster movement of electrons between this region here, between our two oppositely charged plates. And if we further move and increase that frequency, decrease the wavelength, we're seeing these electrons moving at a similar speed. We see a lower current here. Now, depending on the metal, we want to find an appropriate frequency that's going to interact with that particular metal. And that's going to change depending on the metal itself. So initially, these ones started moving. It was about somewhere around the blue-green, so maybe around 500 nanometers. Might have been a little bit longer than that. We're getting a little bit of movement there, albeit not a lot. And we could change these different metals here. So at the same wavelength, 521 nanometers, platinum isn't ejecting any electrons. We could try increasing the intensity. That's not going to do it. So if we try decreasing the wavelength, maybe we'll start to see some. We go into the far ultraviolet range. We have to go pretty short, down to 133 nanometers. Might even be a little bit higher than that to get any movement at all. And this, again, is only at 30%. So depending on the type of emitted radiation and the intensity of that radiation, the photoelectric effect will be slightly different. So we don't get any interaction here. It's kind of hard to do with small numbers, but it's somewhere around 190 or so nanometers where this does begin to start happening. And depending what metals we put here, we can generate different currents. Again, we have that 0.4, almost half a amp worth of current generated here, which is similar to the sodium, but it was at a much longer wavelength. So we can achieve desired outcomes depending on the intensity of this light, and in the case of a solar panel, this flashlight is the sun, and the materials that we put in the solar panel itself to generate the flow of electrons. Now, quantum theory, you've probably heard of this a little bit before. You know, we cover it in chemistry. So quantum theory assumes that electromagnetic energy is emitted from and absorbed by matter in discrete amounts, or what we call packets. And in this particular, this is important to know. Each packet is what we call a quantum or quanta. And we'll see that these quantum or quanta are actual photons. And these photons are going to correlate to, for one example, the creation of light, which we learned about in chemistry. So the amount of energy represented by E of each quantum is directly proportional to the frequency of the electromagnetic radiation. And this is what we call Planck's constant. And it's represented by energy equaling Planck's constant times the frequency of electromagnetic radiation, where E is the energy in joules. Remember, we're always measuring energy in joules. F is the frequency in hertz, and H is Planck's constant. This is found in your reference table. And it's equal to 6.63 times 10 to the minus 34th, very, very small value, joules times seconds. Remember, frequency being 1 per second, or cycles per second, and energy being measured in joules. Now, these small energy values we're going to use electron volts to represent the small values. And remember, 1 electron volt is equivalent to this really small amount of energy, 1.6 times 10 to the minus 19th joules. And these values are found on the front page of your reference table in the table of physical constants. Now the quantum, which is the basic unit of electromagnetic radiation or electromagnetic energy, is called a photon. And matter will absorb and emit these photons in characteristic ways. So although a photon is considered a massless particle of light, it carries both energy and momentum, which is kind of interesting, because if you have momentum, that means you have a mass and a velocity, which is interesting here. So photon is massless. The energy of a photon can be found using the equation Planck's constant times the frequency, which if we break down what the frequency is, can also be represented as Planck's constant times the speed of light divided by the wavelength, which states that the energy of a photon is directly proportional to its frequency and inversely proportional to its wavelength. So if we have a long wavelength, we have lower energy. If we have a short wavelength, we have higher energy. Or if we have a high frequency, we have high energy, or a low frequency, we would have low energy. Now this photoelectric effect demonstrates that if a photon were to strike some piece of metal or a metal surface or a solar panel, that all of the photon's energy is completely absorbed. And therefore would be transferred to the electron that's being ejected from the metal itself. However, when, let's say, a higher energy photon like an X-ray photon with larger energies and larger frequencies than visible light, they strike a metal surface, electrons are given off, as well as electromagnetic radiation of lower frequency. Now we could see this being given off as different colored photons, let's say of visible light, which we saw during chemistry when we looked at the gas discharge tubes of different materials as they were being energized. Now in this scenario, both energy and momentum are both conserved. The incoming or incident photon loses its energy and momentum, while the electron gains that lost energy and momentum. And the momentum of the photon is only going to depend on the wavelength and the frequency. Now we've been talking about particles being treated as particle nature, but they also have, or waves having a particle nature, but particles also have a wave nature. So kind of in reverse here, just as radiation has both wave and particle characteristics, if we consider matter in motion, it's also going to have wave characteristics as well. It's also going to have particle characteristics. It's going to depend on the size or magnitude of the matter that we're looking at. So the wavelength of an ordinary object, let's think of a thrown baseball. If you were to lob a baseball over to a friend or throw a baseball over to a friend, the wavelengths, these are going to be too small to be detected. But waves, if we consider matter that is much smaller, let's say like atomic size, electrons that are being ejected can produce diffraction and interference, which are wave phenomena that provide evidence for the wave nature of particles. So particles having a wave nature is really only going to apply when we look at really small atomic or subatomic particles, which again would have a mass, and as long as they're in motion would portray some of these wave properties as well. So we have a duality here between particles and waves, and they're connected here with Planck's constant, which we'll expand on a little bit further in this unit. If you guys have any questions, make sure you write them down and come see me for any answers. Have a wonderful day.